This video is on the objective calculate the mean and standard deviation of the sampling distribution of sample proportions. And this is number 1. This is the first video on a question related to this objective in your Newton-Alta homework. So let's take a look. So again, hopefully, I'm hoping that you have read section 8.3 in your OpenStax statistics book. Also, if you're looking at this and are unfamiliar with the topic, want to see some more about it, click on more instruction here and look at their notes, their videos, their examples, and hopefully that'll help you out as well. Alright, so we have to remember some things about proportions and sample proportions. So I'm going to refresh your memory here as to what the central limit theorem for proportions stated. It's on a piece of paper. So we have the central limit theorem, remember the CLT for proportions. Remember, proportions was the proportion of successes. You had successes, certain elements in your population that was a success, and certain elements in your population that were considered failures. When I say proportion, I'm talking about the proportion of the population, a percentage that is a success. All right, so remember you have this population. And suppose X represents the number of successes in a population, and we had a lowercase p. Right, the lowercase p represented the proportion of the population that was successful, or that was a success. The proportion of the population that is a success, whatever we deem a success to be, right? So it's the number of people successful, the number of successes in the population divided by, right, the total population size. All right, well then from this, pardon me, from this population, a sample, right, a sample of size n is taken. And again, x here is going to represent the number of successes. And we'll see either now in some of these problems it's going to be p hat or p prime. You might see p prime as well. This is the proportion of the sample that is a success. So the sample proportion. So you might see again p hat or p prime in this section. Now, by the central limit theorem, if the population is normal, or if n times p and n times 1 minus p is greater than or equal to 10, these were like two conditions that needed to hold in order for the central limit theorem to apply, then the distribution of all these p hats, right? Because again, imagine you could look at all possible samples of size n, and you take the sample proportion for all those samples, p hat, p hat, p hat, p hat, p hat, and all those p hats, if either of these conditions are met, would be approximately a normal distribution, with a mean called mu sub p hat, and a standard deviation called sigma sub p hat. where the mean of all these p hats, the mu p hat, is just the population, the proportion of the population, just p. And the standard deviation of all these p hats, these proportions for samples of size n, was the square root of p times 1 minus p, or p times q. I remember you might have seen p times q divided by the sample size, right? All that inside the square root. So hopefully this looks familiar. Right, hopefully this looks familiar. And again, we're talking about normal distributions here. So we'll talk about z-scores later. Right? Yeah. Now, in this section, right, in section 8.3, we are going to be estimating p. We're going to be creating confidence intervals for this population proportion. So very often we are going to be estimating. Right, so we are going to be estimating p with a confidence interval. Right. And the very first guess, right, our point estimate, is going to be our sample proportion, our p hat or our p prime. And that will replace p. Right, so again, we'll approximate this with p hat. Use a point estimate for p. And again, we'll approximate this standard deviation with the square root of p hat times, I'll say q hat, which is 1 minus p hat divided by n. And we're going to use approximations to these. So that's what you're asked to be doing. That's what we're going to be asked about in this first objective. Right, what is the mean of the distribution of the sample proportions, this mu sub p hat, where we're going to approximate it with? And what is the standard deviation of this distribution of sample proportions? What's this sigma p hat? What are we going to approximate it with? All right, so let's go back to this question. So here, an entertainment company surveyed 360 elementary school children and found that 153 of them were above grade level readers. So find the standard error, or standard deviation, for the sample proportion of elementary school children who were above grade level readers. And enter your answer as a decimal rounded to 3 decimal places. All right. So, back on some paper here, I'll write down the information that was just given to us. So we are told that the sample size here, sample taken from the population of all elementary school children, they took 360 of these elementary school children. N is 360. Now, a success in this question, what they mean by success is reading above grade level. And remember, I'll let X represent the number of successes. So in this particular sample, right, they said of these 360 elementary school children, they found that 153 of them were above grade level readers. So the number of successes is 153. All right, so then we can get our sample proportion. Right, the p hat or p prime for this, remember, it's just the number of successes divided by the sample size. So 153 out of the 360 children were above grade level readers, right? Were successful, considered successes. And I'll leave it like this. Now you could round it. I'll put it in a calculator. We'll round to a bunch of decimal places. You'll pull a calculator up. And we take 153 successes divided by the 360 kids. So our sample, I don't need to round, it's perfectly even. So our sample proportion, our p hat, is 0.25. All right. Now again, by our central limit theorem, The distribution of all the sample proportions for samples of size 360 should be normally distributed with a mean, mu p hat, and a standard deviation sigma p hat, where the mean of these sample proportions should be equal to the population proportion. But as I mentioned before, this population proportion I do not know. Right? We were not told what percentage of all elementary school children read above grade level. We're only given the percentage of this sample. So we're going to use our point estimate. We're going to use our sample proportion, our 0.425, as a point estimate for P. All right, and the same thing for this standard deviation, or the standard error of these sample proportions of these p hats. All the p hats, all the possible p hats for all the possible samples of size 360, that's the square root of, again, p. Normally it would be p times 1 minus p divided by n, but I don't know what p is. Again, I have no idea what the population proportion is. So we're going to estimate it with our p hat. So we'll use this, instead of that, we'll use the square root of 0.425 times 1 minus 0.425 would be 0.575, and then divided by the sample size, right? Divided by 360. And this is what we're asked for here. This is the standard deviation of the p hats, or the standard error. You might see it referred to as the standard error of the sample proportions as well. All right, so I'm going to enter this value, this square root of 0.425 times 0.575 divided by 360, and make sure that's all inside the square root. Right? So square root 0.425 times 0.575 divided by 360, and again, make sure all of that is underneath the square root. So we're getting a standard error, standard deviation for all these p hats of 0. And they asked us to round to 3 decimal places, so 0.026. And this is all they're asking for. The standard deviation of this distribution of the sample proportions, the distribution of the p hats. Okay, so standard error, as I said, 0.026 to 3 decimal places. Submit. Wonderful. And again, they go through the same calculations I went through. Read your answer explanations. See, they're using p prime sometimes instead of p hat. Same thing, right? You see the p prime or the p hat with the little wedge on top. It means the same thing. All right. And yeah, they're going through the same exact calculation I just showed you. Okay. So this is just one question. I'll probably get another video on another question like this later. Hopefully this helps you out when working on this kind of stuff on your own. And thank you very much for watching.